Part 4 of Cosmos, a sketch of the physical description of the universe, Introduction, by Alexander von Humboldt. This LibriVox recording is in the public domain. Physical astronomy presents us with other phenomena which cannot be fully comprehended in all their vastness without a previous acquirement of general views regarding the forces that govern the universe. Such, for instance, are the innumerable double stars, or rather suns, which revolve around one common center of gravity, and thus reveal in distant worlds the existence of the Newtonian law. The larger or smaller number of spots upon the sun, that is to say, the openings formed through the luminous and opaque atmosphere surrounding the solid nucleus, and the regular appearance about the 13th of November and the 11th of August of shooting stars, which probably form part of a belt of asteroids intersecting the Earth's orbit and moving with planetary velocity. Descending from the celestial regions to the earth, we would fain inquire into the relations that exist between the oscillations of the pendulum in air, the theory of which has been perfected by Bessel, and the density of our planet, and how the pendulum, acting the part of a plummet, can, to a certain extent, throw light upon the geological constitution of strata at great depths. By means of this instrument we are enabled to trace the striking analogy which exists between the formation of the granular rocks composing the lava currents ejected from active volcanoes, and those endogenous masses of granite, porphyry, and serpentine, which, issuing from the interior of the earth, have broken as eruptive rocks through the secondary strata, and modified them by contact, either in rendering them harder by the introduction of silex, or reducing them into dolomite, or finally by inducing within them the formation of crystals of the most varied composition. The elevation of sporadic islands, of domes of trachyte, and cones of basalt by the elastic forces emanating from the fluid interior of our globe, has led one of the first geologists of the age, Leopold von Buch, to the theory of the elevation of continents and of mountain chains generally. This action of subterranean forces in breaking through and elevating strata of sedimentary rocks, of which the coasts of Chile, in consequence of a great earthquake, furnished a recent example, leads to the assumption that the pelagic shells found by M. Bonpland and myself on the ridge of the Andes, at an elevation of more than 15,000 English feet, may have been conveyed to so extraordinary a position, not by a rising of the ocean, but by the agency of volcanic forces capable of elevating into ridges the softened crust of the earth. I apply the term volcanic, in the widest sense of the word, to every action exercised by the interior of a planet on its external crust. The surface of our globe and that of the moon manifest traces of this action, which in the former at least has varied during the course of ages. Those who are ignorant of the fact that the internal heat of the earth increases so rapidly with the increase of depth that granite is in a state of fusion about 20 or 30 geographical miles below the surface, cannot have a clear conception of the causes and the simultaneous occurrence of volcanic eruptions at places widely removed from one another, or of the extent and intersection of circles of commotion in earthquakes, or of the uniformity of temperature and equality of chemical composition observed in thermal springs during a long course of years. The quantity of heat peculiar to a planet is, however, a matter of such importance, being the result of its primitive condensation, and varying according to the nature and duration of the radiation, that the study of this subject may throw some degree of light on the history of the atmosphere, and the distribution of the organic bodies embedded in the solid crust of the earth. This study enables us to understand how a tropical temperature, independent of latitude, that is, of the distance from the poles, may have been produced by deep fissures remaining open and exhaling heat from the interior of the globe, at a period when the earth's crust was still furrowed and rent, and only in a state of semi-solidification. and a primordial condition is thus revealed to us, in which the temperature of the atmosphere, and climates generally, were owing rather to a liberation of caloric and of different gaseous emanations, that is to say, rather to the energetic reaction of the interior on the exterior, than to the position of the earth with respect to the central body, the sun. The cold regions of the earth contain, deposited in sedimentary strata, the products of tropical climates. Thus, in the coal formations, we find the trunks of palms standing upright, amid conifers, tree ferns, goniotites, and fishes having rhomboidal osseous scales. In the Jura limestone, colossal skeletons of crocodiles, plesiosauri, planulites, and stems of the cicadae. In the chalk formations, small polythalamia and bryozoa, whose species still exist in our seas. In tripoli, or polishing slate, in the semi-opal and the farina-like opal, or mountain meal, agglomerations of siliceous infusoria, which have been brought to light by the powerful microscope of Arenberg. And lastly, in transported soils, and in certain caves, the bones of elephants, hyenas, and lions. An intimate acquaintance with the physical phenomena of the universe leads us to regard the products of warm latitudes that are thus found in a fossil condition in northern regions, not merely as incentives to barren curiosity, but as subjects awakening deep reflection and opening new sources of study. The number and the variety of the objects I have alluded to give rise to the question whether general considerations of physical phenomena can be made sufficiently clear to persons who have not acquired a detailed and special knowledge of descriptive natural history, geology, or mathematical astronomy. I think we ought to distinguish here between him whose task it is to collect the individual details of various observations, and study the mutual relations existing among them, and him to whom these relations are to be revealed under the form of general results. The former should be acquainted with the specialities of phenomena, that he may arrive at a generalization of ideas as the result, at least in part, of his own observations, experiments, and calculations. It cannot be denied that where there is an absence of positive knowledge of physical phenomena, the general results which impart so great a charm to the study of nature cannot all be made equally clear and intelligible to the reader, but still I venture to hope that in the work which I am now preparing on the physical laws of the universe, the greater part of the facts advanced can be made manifest without the necessity of appealing to fundamental views and principles. The picture of nature thus drawn, notwithstanding the want of distinctness of some of its outlines, will not be the less able to enrich the intellect, enlarge the sphere of ideas, and nourish and vivify the imagination. There is perhaps some truth in the accusation advanced against many German scientific works, that they lessen the value of general views by an accumulation of detail, and do not sufficiently distinguish between those great results which form, as it were, the beacon lights of science, and the long series of means by which they have been attained. This method of treating scientific subjects led the most illustrious of our poets to exclaim with impatience, "The Germans have the art of making science inaccessible." An edifice cannot produce a striking effect until the scaffolding is removed, that had of necessity been used during its erection. Thus the uniformity of figure observed in the distribution of continental masses, which all terminate toward the south in a pyramidical form and expand toward the north, a law which determines the nature of climates, the direction of currents in the ocean and the atmosphere, and the transition of certain types of tropical vegetation toward the southern temperate zone, may be clearly apprehended without any knowledge of the geodesical and astronomical operations by means of which these pyramidical forms of continents have been determined. In like manner, physical geography teaches us by how many leagues the equatorial axis exceeds the polar axis of the globe, and shows us the mean equality of the flattening of the two hemispheres, without entailing on us the necessity of giving the detail of the measurement of the degrees in the meridian, or the observations on the pendulum which have led us to know that the true figure of our globe is not exactly that of a regular ellipsoid of revolution, and that this irregularity is reflected in the corresponding irregularity of the movements of the moon. The views of comparative geography have been specially enlarged by the admirable work Erkunde im Verhältnis zur Natur und zur Geschichte, in which Karl Ritter so ably delineates the physiognomy of our globe, and shows the influence of its external configuration on the physical phenomena on its surface, on the migrations, laws, and manners of nations, and on all the principal historical events enacted upon the face of the earth. France possesses an immortal work, L'expression du Système du Monde, in which the author has combined the results of the highest astronomical and mathematical labors, and presented them to his readers free from all processes of demonstration. The structure of the heavens is here reduced to the simple solution of a great problem in mechanics, yet Laplace's work has never yet been accused of incompleteness and want of profundity. The distinction between dissimilar subjects and the separation of the general from the special are not only conducive to the attainment of perspicuity in the composition of a physical history of the universe, but are also the means by which a character of great elevation may be imparted to the study of nature. By the suppression of all unnecessary detail, the great masses are better seen, and the reasoning faculty is enabled to grasp all that might otherwise escape the limited range of the senses. The exposition of general results has, it must be owned, been singularly facilitated by the happy revolution experienced since the close of the last century in the condition of all the special sciences, more particularly of geology, chemistry, and descriptive natural history. In proportion as laws admit of more general application, and as sciences mutually enrich each other, and by their extension become connected together in more numerous and more intimate relations, the development of general truths may be given with conciseness devoid of superficiality. On being first examined, all phenomena appear to be isolated, and it is only by the result of a multiplicity of observations, combined by reason, that we are able to trace the mutual relations existing between them. If, however, in the present age, which is so strongly characterized by a brilliant course of scientific discoveries, we perceive a want of connection in the phenomena of certain sciences, we may anticipate the revelation of new facts, whose importance will probably be commensurate with the attention directed to these branches of study. Expectations of this nature may be entertained with regard to meteorology, several parts of optics, and to radiating heat and electromagnetism, since the admirable discoveries of Melloni and Faraday. A fertile field is here open to discovery, although the voltaic pile has already taught us the intimate connection existing between electric, magnetic, and chemical phenomena. Who will venture to affirm that we have any precise knowledge, in the present day, of that part of the atmosphere which is not oxygen, or that thousands of gaseous substances affecting our organs may not be mixed with the nitrogen, or finally that we have even discovered the whole number of the forces which pervade the universe? It is not the purpose of this essay on the physical history of the world to reduce all sensible phenomena to a small number of abstract principles based on reason only. The physical history of the universe, whose exposition I attempt to develop, does not pretend to rise to the perilous abstraction of a purely rational science of nature, and is simply a physical geography combined with a description of the regions of space and the bodies occupying them. Devoid of the profoundness of a purely speculative philosophy, my essay on the Cosmos treats of the contemplation of the universe, and is based upon a rational empiricism, that is to say, upon the results of the facts registered by science and tested by the operations of the intellect. It is within these limits alone that the work which I now venture to undertake appertains to the sphere of labor to which I have devoted myself throughout the course of my long scientific career. The path of inquiry is not unknown to me, although it may be pursued by others with greater success. The unity which I seek to attain in the development of the great phenomena of the universe is analogous to that which historical composition is capable of acquiring. All points relating to the accidental individualities and the essential variations of the actual, whether in the form and arrangement of natural objects, in the struggle of man against the elements, or of nations against nations, do not admit of being based only on a rational foundation, that is to say, of being deduced from ideas alone. It seems to me that a like degree of empiricism attaches to the description of the universe and to civil history, but in reflecting upon physical phenomena and events, and tracing their causes by the process of reason, we become more and more convinced of the truth of the ancient doctrine that the forces inherent in matter, and those which govern the moral world, exercise their action under the control of primordial necessity and in accordance with movements occurring periodically after longer or shorter intervals. It is this necessity, this occult but permanent connection, this periodical recurrence in the progressive development of forms, phenomena, and events, which constitute nature, obedient to the first impulse imparted to it. Physics, as the term signifies, is limited to the explanation of the phenomena of the material world by the properties of matter. The ultimate object of the experimental sciences is, therefore, to discover laws and to trace their progressive generalization. All that exceeds this goes beyond the province of the physical description of the universe and appertains to a range of higher speculative views. Immanuel Kant, one of the few philosophers who have escaped the imputation of impiety, has defined with rare sagacity the limits of physical explanations in his celebrated essay On the Theory and Structure of the Heavens, published at Königsberg in 1755. The study of a science that promises to lead us through the vast range of creation may be compared to a journey in a far distant land. Before we set forth, we consider, and often with distrust, our own strength and that of the guide we have chosen. But the apprehensions which have originated in the abundance and the difficulties attached to the subjects we would embrace recede from view as we remember that with the increase of observations in the present day there has also arisen a more intimate knowledge of the connection existing among all phenomena. It has not unfrequently happened that the researches made at remote distances have often and unexpectedly thrown light upon subjects which had long resisted the attempts made to explain them within the narrow limits of our own sphere of observation. Organic forms that had long remained isolated both in the animal and vegetable kingdom have been connected by the discovery of intermediate links or stages of transition. The geography of beings endowed with life attains completeness as we see the species, genera, and entire families belonging to one hemisphere reflected, as it were, in analogous animal and vegetable forms in the opposite hemisphere. These are, so to speak, the equivalents which mutually personate and replace one another in the great series of organisms. These connecting links and stages of transition may be traced alternately in a deficiency or an excess of development of certain parts, in the mode of junction of distinct organs, in the differences in the balance of forces, or in a resemblance to intermediate forms which are not permanent, but merely characteristic of certain phases of normal development. Passing from the consideration of beings endowed with life to that of inorganic bodies, we find many striking illustrations of the high state of advancement to which modern geology has attained. We thus see, according to the grand views of Elie de Beaumont, how chains of mountains, dividing different climates and floras, and different races of men, reveal to us their relative age, both by the character of the sedimentary strata they have uplifted, and by the directions which they follow over the long fissures with which the earth's crust is furrowed. Relations of superposition of trachyte and of senitic porphyry, of diorite and of serpentine, which remain doubtful when considered in the auriferous soil of Hungary, in the rich platinum districts of the Ural, and on the southwestern declivity of the Siberian Altai, are elucidated by the observations that have been made on the plateaus of Mexico and Antioquia, and in the unhealthy ravines of Choco. The most important facts on which the physical history of the world has been based in modern times have not been accumulated by chance. It has at length been fully acknowledged, and the conviction is characteristic of the age, that the narrative of distant travels, too long occupied in the mere recital of hazardous adventures, can only be made a source of instruction where the traveler is acquainted with the condition of the science he would enlarge, and is guided by reason of his researches. It is by this tendency to generalization, which is only dangerous in its abuse, that a great portion of the physical knowledge already acquired may be made the common property of all classes of society. But in order to render the instruction imparted by these means commensurate with the importance of the subject, it is desirable to deviate as widely as possible from the imperfect compilations designated, till the close of the 18th century, by the inappropriate term of popular knowledge. I take pleasure in persuading myself that scientific subjects may be treated of in language at once dignified, grave, and animated, and that those who are restricted within the circumscribed limits of ordinary life, and have long remained strangers to an intimate communion with nature, may thus have opened to them one of the richest sources of enjoyment, by which the mind is invigorated by the acquisition of new ideas. Communion with nature awakens within us perceptive faculties that had long lain dormant, and we thus comprehend at a single glance the influence exercised by physical discoveries on the enlargement of the sphere of intellect, and perceive how a judicious application of mechanics, chemistry, and other sciences may be made conducive to national prosperity. A more accurate knowledge of the connection of physical phenomena will also tend to remove the prevalent error that all branches of natural science are not equally important in relation to general cultivation and industrial progress. An arbitrary distinction is frequently made between the various degrees of importance appertaining to mathematical sciences, to the study of organized beings, the knowledge of electromagnetism, and investigations of the general properties of matter in its different conditions of molecular aggregation. And it is not uncommon presumptuously to affix a supposed stigma upon researches of this nature by terming them purely theoretical, forgetting, although the fact has long been attested, that in the observation of a phenomenon which at first sight appears to be wholly isolated, may be concealed the germ of a great discovery. When Aloysius Galvani first stimulated the nervous fiber by the accidental contact of two heterogeneous metals, his contemporaries could never have anticipated that the action of the voltaic pile would discover to us in the alkalies metals of a silvery luster, so light as to swim on water and eminently inflammable, or that it would become a powerful instrument of chemical analysis, and at the same time a thermoscope and a magnet. When Huygens first observed in 1678 the phenomenon of the polarization of light, exhibited in the difference between the two rays into which a pencil of light divides itself in passing through a doubly refracting crystal, it could not have been foreseen that a century and a half later the great philosopher Arago would, by his discovery of chromatic polarization, be led to discern, by means of a small fragment of Iceland spar, whether solar light emanates from a solid body or a gaseous covering, or whether comets transmit light light directly or merely by reflection. An equal appreciation of all branches of the mathematical, physical, and natural sciences is a special requirement of the present age, in which the material wealth and the growing prosperity of nations are principally based upon a more enlightened employment of the products and forces of nature. The most superficial glance at the present condition of Europe shows that a diminution or even a total annihilation of national prosperity must be the award of those states who shrink with slothful indifference from the great struggle of rival nations in the career of the industrial arts. It is with nations as with nature, which, according to a happy expression of Goethe, knows no pause in progress and development, and attaches her curse on all inaction. The propagation of an earnest and sound knowledge of science can therefore alone avert the dangers of which I have spoken. Man cannot act upon nature or appropriate her forces to his own use without comprehending their full extent, and having an intimate acquaintance with the laws of the physical world. Bacon has said that in human societies knowledge is power. Both must rise and sink together. But the knowledge that results from the free action of thought is at once the delight and the indestructible prerogative of man, and in forming part of the wealth of mankind, it not unfrequently serves as a substitute for the natural riches, which are but sparingly scattered over the earth. Those states which take no active part in the general industrial movement, in the choice and preparation of natural substances, or in the application of mechanics and chemistry, and among whom this activity is not appreciated by all classes of society, will infallibly see their prosperity diminish in proportion as neighboring countries become strengthened and invigorated under the genial influence of arts and sciences. End of Part 4.